welcome to our power quality improvement technique program on NPTEL. We shall continue with the overview which was discussing in previous class. So, now we will talk about the sag and the dips. We have already defined the sag. Now, we shall little bit elaborate a different kind of sags. So, as we have mentioned that sag is a decrease of the voltage between 0.1 to 0.9 pu per unit in RMS value of the current at the power frequency and during the period of at least 0.5 cycle. Then we will consider this entry to be sag until 1 minute. If it is consisting of longer than 1 minute, you can take it as an interruption. And the causes of the voltage sag is associated with the faults, mainly energization of the heavy load, starting of the large motors. These are, the starting current of the induction motor is very high. For example, here we shall first show you this is a per unit voltage. Here the all of a sudden we have a single line to ground fault, and thus voltage has been sagged and thereafter it has been recovered, and this is the voltage profile. So, this is RMS value and this is the waveform during the sag, that till that point it was healthy. So, thereafter there is initiation of the sag and then it has been corrected here. So, from this point onward, so corrective action was taken. So, you can see that this is the picture. So, this phenomena is been categorized as a sag. Similarly, we shall illustrate another figure that illustrates that effect of the large motor starting. An induction motor will draw 6 to 7 times of its full load current during the startup, and due to that the voltage will fall. You can see that this is the moment current voltage motor has been started. So, there will be a fall in the voltage from 100% to 80% and gradually it will reach the value. This is the time scale is in second. As shown here, in this case the voltage sags immediately to the 80% and then gradually returns after its normal value and after 3 seconds. So, this is the case here where voltage sag may occur. So, based on that different kind of sag, so note that difference in time frame between these sags due to utility system faults that has to be categorized. So, sag durations are subdivided here into 3 categories such as instantaneous sags, that is for 0.5 cycles to 30 cycles, and momentarily sags, that is for 30 cycles to the 3 seconds, and the temporary sags, that is for the longer duration, this is for the 3 seconds to 1 minute. So, this is something you will categorize. Similarly, the voltage built up, it is said to be the swell. A swell is defined as an increase in voltage between 1.1 to 1.8 per unit in RMS voltage or current at the power frequency for the duration of minimum 0.5 cycles to 1 minute. Swells characterized by the magnitude of the RMS value and also the duration, same thing, but instead of the 3 minutes we can allow only 1 minute. So, cause of the swell, it will be associated with the system faults. So, once you got a system fault and you have open up a line, there will be open circuit case. Open circuit case will reflect back the wave and thus it may cause high voltage. And energization of the large capacitor bank, that is also a cause. So, we discussed in the fax devices how to energize the capacitor bank. Otherwise, because you have to start, you require to see that the capacitor voltage, return capacitor voltage and the supply voltage are same, then only you are going to switch it on. Otherwise, it gives a transient, and this transient, if it is not undamped, then it will cause a sustained oscillations of high voltage. And just reverse, we have seen that switching on the large load, and it can be a swell because of the switching off large load. Once all of a sudden you switch off, so voltage will build up. Similarly, we require to see and identify the severity of the voltage swell during a fault condition as a function of fault location, where does it located, where the open circuit occurs, fault system impedance and the ground impedance. Here, for example, instantaneous voltage swell caused by a single line to the ground fault in other two line. So, all of a sudden there is a distortion, and thus you can see that voltage has swelled, then it has again sagged. This phenomena occurs to other healthy line in case of the single line to ground fault. So, another is that negative sequence due to the unbalance. That negative or the zero sequence present only in 3-phase 4-wire system in a distribution network, otherwise zero sequence is absent. We shall discuss in detail about the zero sequence component and the negative sequence component in shunt active power filter. You can refer back that lectures once it has been delivered to you. So, zero sequence voltage in a power systems is generally results from the unbalanced loads causing negative or the zero sequence current to flow. So, voltage unbalance equal to 100% into maximum deviation from the average voltage by average voltage, or you can take RMS voltage also, where the average voltage is equal to sum of the voltage in 3 phases. So, generally we have some condition of fault tolerance, single load on a 3-phase circuits, we should have a negative sequence less than 2%, that we accept. The result of blown fuse in one phase of the 3-phase capacitor bank, this may cause a severe unbalance, and when it is the capacitor bank, it may blow out the fuses, and severe unbalance, that is more than 5%, can result from the single phasing condition. That I will show that how even the typical single phasing conditions also can be mitigated by the shunt active power filter. So, recall this lectures, this condition there. So, we are showing that V0 by V1 and V2, this is the case of the unbalanced voltage in percentage in residential feeder of date wise, and you can see that this is the hour wise, this amount is a 24 hours. Once there is a peak, there is a 2 peak in India, and generally it is in morning and 8 to 10 am, and it is after 6 to 9 pm. So, for this reason you can see that both this peak, when the peak demand is more, also unbalance also going to be more, and this is the case of the feeder of 2 feeder V0 by V1 and V2 by V1 for the residential figure. So, this is the way it changes over the time span while you have an unbalanced load into the distribution system. So, let us define those waveform distortion. It is defined as a steady state variation from an ideal sine wave of power frequency, principally characterized by the spectral content of the deviation. So, you can have a spectral analysis and you see that whether you got a fundamental, that is all. If you are getting a fundamental, it is fine. Otherwise, there is a 5 type of wave distortion. This is DC offset. Generally, it presents when your positive area and the negative area does not match. So, you have some average value. There are harmonics. Once you have a nonlinear transformation from AC to DC, then in AC side, then it will be injecting the harmonics. So, for this, and there are different kind of harmonics. So, special type of harmonics are called interharmonics, that we shall discuss in detail, and what is the effect of it and why it is arises into the system. There are notch and noises. Noise can be wideband noise and other noises that can present into the system. DC offset, the presence of the DC offset voltage or the current are as an AC power system term as a DC offset. You mean to say you can feed a DC voltage, thereafter you can have a AC. So, resultant will be this. So, this amount is a DC offset, or you can have a positive area and negative area mismatch, then also you can have a DC offset. Generally, it happens when you have a triggering pulses are not same and you require to compensate that with the time. Generally, DC offset can be eliminated by properly switching the thyristor based devices and keeping the positive area and the negative area same. The harmonic, this is something a most dominating entity in the power quality. Harmonics are sinusoidal voltage or current having frequencies that are integral multiple of the frequencies at which the supply system designed to operate. IEEE standard 51910, this is basically the 1992 standard. Further standard has been elevated, provide guideline for the harmonic current and the voltage distortion level on the distribution and the transmission circuit. This is generally a research guideline, but we have a separate guideline for and a separate gate for the different country, but generally it adhered to the IEEE standard. Thereafter, periodically distorted waveforms, though that is something a very important distortion phenomena can be noticed, can be decomposed into the sum of the fundamental frequency and the harmonics. That is, you can have this waveform, this is a square wave waveform, it is not distorted, but you can say that distorted sine waveform, and that can be split it into the sine and cosine component and with its corresponding harmonics in a Fourier series. Harmonic distortion originates in nonlinear characteristics of the device and loads on the power system. Once you have a diode based rectifier, thyristor, AC to DC converter, all will cause harmonic distortion. Harmonic distortion level are described by the complete harmonic spectrum with magnitude and phase angle of each individual harmonics component. So, we will split like this. Now, few term which you are familiar with for a long time, but we just sake of recall we are describing here. These are total harmonic distortion, THD, as a measure of the effective value of the harmonic distortion, and THD is one of the prime criteria in power quality. It is used to characterize both current and voltage waves. However, THD refers distortion of the voltage wave sometime if you talk about the voltage THD, and we shall next figure illustrate the waveform of the adjustable speed drive. This is something which you will see that we have a diode based rectifier followed by a capacitor, then a adjustable speed drive. So, you can see the few things. So, that is the maximum voltage is this, minimum voltage is this, average is this, RMS is this, form factor is this, and you can have a frequency of 60 hertz, fundamental value is 19 point something, THD here you will find it is more than 8 times more than the standard applicable value, that is 41%, and RMS value is definitely of this 7.9 and RMS is 21.1 and TIF is the 72.5 factors. So, this is the fundamental. Thereafter this will come, generally does not come, it is coming due to the your quantization error of your sensors, and generally these are very negligible and it comes due to the noises. So, this is essentially a fifth harmonic, this is essentially seventh harmonic, thereafter you have a 11 and 13 harmonic and so on. This will be the harmonic spectrum for adjustable speed drive. So, the total harmonic distortion according to the IEEE 519 sets a limit of the total harmonic distortion for the utility side of the meter. It is restricted generally 5%. Utility is responsible for the voltage distortion at the point of the common coupling, that is we will abbreviate as PCC in our further course of action between the utility and the user. The total harmonic distortion is a way to evaluate the voltage distortion effect of injecting harmonic current into the utility system. So, it is the cause of the nonlinear load. Your voltage may be fine sinusoidal, but your current has got a distortion. So, the total harmonic distortion of RMS of the harmonic current, it is RMS value of the fundamentals by 100%. So, we can define as IH equal to, except fundamental, it is I2 square plus I3 square and so on, and THD it can be represented by 100%, that has been shown, or otherwise this is the amount of the harmonic. So, that can be defined as a harmonic. For example, I am giving you one example. Find the total harmonic distortion of the voltage waveform with the following harmonic pickup. Generally what happen, you may have a source and you will have a source inductance mostly, because you feed it with the transformer and all, and that all has a leakage reactance, and transmission line itself is inductive. And thereafter when you have a diode bridge rectifier and thus you have a current that is fundamental, thereafter 5th, 7th, 11, 13, and if you have 3-phase 4-wire system, then also the third harmonic, and that also once it current flows, the third harmonic current flows to the inductor that gives to this voltage. 5th harmonic current, once it flows through this inductor, it goes to this 5th harmonic voltage and so on. So, let us see that this is a way to calculate, it is very easy. So, VH will be under root of 4 square plus 2 square plus 1 square plus A. So, this will be your voltage harmonic. So, voltage TSD you can define it as 4.82 by 114 into 100, that is 4.23% is your voltage TSD, and it is some extent acceptable. Now, total demand distortion, this is something you may not come across very easily, this is a commercial term we use sometime in utility. So, 519 IEEE 519 also sets the limits of total demand distortion, that is for the end user meter. So, how much demand you want and how much distorted power factor you get. So, this is something, the RMS of the harmonic current by RMS value of the meter load current into the 100%. So, this is we say that as a TDD. So, sometimes it is also important. So, how much meter current I am getting, it may be actually not unity power factor, it may be some other power factor. So, all has to be taken into the account. It is expressed in percentage of the rated load current, because that is what we are aware of. Because once we have chosen a meter that based on the kVA rating, but since voltage is fixed, so ultimately your load current is something that varies. If you take a 3 kVA meter, so your load current is limited to around 15 ampere. If you are taking a 6 kVA meter, load current is around 30 ampere. So, these are all single phase currents with some amount of tolerance. So, thereafter after 6 kV we generally have a 3 phase current, 3 phase meters. So, there also we have to take into this account. So, TDD, that is the new entity we will come across, and the utility doesn't speak about the THD. Utility generally speaks about the total demand distortion. You demand this much, I feed this much of the distorted power. Deals with the evaluating the current distortion caused by the harmonic current to the end user facilities, and all these legal implications are with the TDDs. So, what is TDDs? It is basically harmonic current by the demanded load current, where, so if you are not taking your full load current, if your harmonic content is more, then you cannot penalize your utility or take a legal action against it. But if it is reverse, then you can, of course, when you are drawing the full load current, then it will be measured at the full load current. So, that is, we say IL equal to the RMS value of the maximum demand load current, and this is a harmonic content, and IH is the RMS of the harmonic current except fundamentally. So, let us come into the new entity that is called interharmonic. So, interharmonics is a new entity, and it happens, you know, you know that we have a 50 hertz, and generally if you go to USA you have a 60 hertz, and maybe you have taken a device from imported device from the USA, which is carrier frequency is 720 hertz. So, that is quite acceptable, because it is basically it is a harmonic of 60 hertz, but it is not harmonic of 60 hertz, it will be interharmonic of the 60 hertz. So, same devices, once you try to run in to the 50 hertz system, then you will have this problem. So, what happen? The voltage or current having frequency component that are not integer multiple of the fundamental frequency, these are called the interharmonics. 720 hertz is not integer multiple of 50 hertz. So, once you run it, you just try it out, you run you take a switching frequency of a simple PWM inverter 3 phase with 720 hertz, and your modulating frequency is 50 hertz, and try to see in MATLAB Simulink what spectrum you are getting. And if you make just 13 times of it, generally we advise to have odd numbers of the 15 hertz. So, and see that what is the difference of the change you are making, and that is something you will observe a very interesting phenomena, and there this interharmonic you will be introducing if you take the switching frequency around 720 Hz. If it is present, it is very difficult to eliminate, and sometimes it rises to the subharmonics, because ultimately your power system is a low pass filter, thus high frequency does not have much problem. More it will eliminate the low pass element, but due to the interharmonics, sometimes low frequency comes into the picture, subharmonics. So then you have a lot of problem to eliminate them. So we generally do not use the interharmonics while choosing the PWM and all. If it is arises, then it is very nasty element, and eliminating this entity is quite difficult. And what is the source of this waveform? Static frequency converter, matrix converter. Matrix converter, it converts, if you are converting to 50 Hz, if you are generally we have generally we can have a wind energy conversion system for, and their wind speed varies. It may be 11 Hz to 20 Hz, and except 25 Hz, all the inputs are not integral multiple of the 50 Hz. Then what will happen? Then it leads to the some extent the interharmonics into this output of this waveform 50 Hz, and if comes sometime, if it is not properly tuned, then this will raise to the interharmonics and thus cause a low frequency. After filter, you can filter out the high frequency part, thereafter you will find that low frequency part is present. So this is one of the detrimental issues in the power quality problem. Once you are converting to, or you are having a V by F control, then also this case arises by the matrix converter. So same way for the cyclo converter for the little higher power devices, because it's an induction furnace and arc devices, this may leads to the interharmonics. Thereafter you come to the notches. The notching is a periodic waveform disturbance caused by the normal operation of the power electronics devices when current is commutated to one phase to another. That it can be seen quite well in case of the most of the converter, and once it goes to this phase, to once after 60° a pair of thyristors is conducting, then it will switch over to the another pair of thyristors. Each of the case will gives you a notch. So this waveform, if it is there, we require to eliminate the notch. That is also the comes under the purview of the power electronics, and also we require to eliminate it by the power quality. Thank you for your attention. I shall continue to the overview. I require another 2 classes to capture the holistic view of the power quality. In next class, I also continue with this different aspect of the notches and power quality issues. Thank you.